Okay, go.
So today I want to talk about the Zhaozhou Bridge. So next I want to show you some slides about the Zhaozhou Bridge.
Yeah. Do you like the animation?
Yes.
Cool.
Okay, so now I would like to take on. So
Wait, I forgot to introduce like the name of our group. So like the name of last group is like Pizza Hut. So like the name of our group is Cambridge, because like the Cambridge shares the same pronunciation with build a bridge in Chinese. So it's just like a playful pun. Yeah, and during this presentation, we'll give you guys a brief but like detailed summary about our research into the mechanical performances of Zhaozhou Bridge. So yeah, Daniel.
all right, here we go. Here's this. Yeah, we have seen this slide. This is basically the bridge, and that's our topic. I'm going to talk about the background information of the bridge. Now we start. So the bridge basically has two names, like in sense. So some people call it Anji Bridge because in Chinese, in the literal translation for the Chinese, it's going to be the safe crossing bridge. And also because a bridge is made out of a lot of stones, like literally all the components are limestones, and they're compacted together, so it earns another name of Great Stone Bridge. And also, we have this guy here. This guy is called Ling Shen, and he's basically the architect. Architecture. He built this bridge as well as he planned everything about this bridge, and he also considered it as I guess like a father of the bridge. And afterwards, we have the history of the bridge. The history is basically during the Kanghe period, which lasts from 595 to 605 CE, and basically during those times, what happens after the decline of the previous town's dynasty, basically they try to restore the whole process of the public work. So they built this bridge for everyone's benefit. Okay, now we have this geographical information here. So basically the bridge is located at Anji. It's like located in Hebei, basically, in Hebei provinces. I've got no idea why this one doesn't work, like should play like slide by slide, but okay, so basically this is a map of China, right? And then now we have this Hebei here, province here, and then the Anji Bridge is located like inside of it. And don't get confused, because this another place also called Anji, and then it's located in Zhejiu province. So like, don't get confused. Even though it's called Anji Bridge, it's because of its name of Safe Crossing Bridge. And also, so this bridge basically crosses the Xiaohe River, and by the bank side of the rivers, basically what they have was this very coarse stones and sands, and then they are very incompressible because they basically have a layer of the salty clay as well as a layer of salty sands, and they're distributed equally. And because the property of the salty clay, it's very hard and it's incompressible. It basically supports the bridge like quite well. So even when students have experiences the flood or the earthquake, like it still won't fundamentally destroy it at the base, because it's you can't liquefaction of the soil cannot happen. And unfortunately, I've got no idea why this slide doesn't work. Basically, this slide, it shows a hamburger of the clay, the salty clay, as well as the salty sand. So the salty clay, it's like hamburgering or sandwiching the salty sands. It's probably like what the previous group also has mentioned. It's also like it's like a burger. And yeah, so if we have a bridge on top of this, and then the salty sand and the salty clays are impressible, you can't compress them. So basically, they're going to be stable. The bridge is going to stay stable on top of it. And you can skip. So I've got no idea, the slide doesn't work. Okay, so basically what we have here was, so we have this is our whole entire bridge. And I would like to talk about the spectrum. So the spectrum basically is symmetrical. So we have both sides. On each side, we have two pairs. We basically have two pairs. So we literally have four spectrums, open spectrums, and they function quite well, because during 1,400 years of this bridge history, like there has been numerous flood going on. So this whole spectrum basically opens up space for the water to pass through by almost 16.5%. And also, this is going to be a smart decision, because during the earthquake, you want to have less material. So basically, this saves up about 7.85% of materials. Basically means 700 tons of material of limestone saved. And I would like to talk about the arc. So the arc, basically, the arc length is going to be 37.2 meters apart for the spans, as well as the height is going to be 7.23 meters height. So the width of the bridge doesn't really matter, but it's 9 meters. So if we compare this bridge to another bridge which has a symmetrical bridge, so basically this bridge only cuts 83 degrees angle from the whole circle. So if you were to imagine like there would be a circle like down here, this is only going to be 83 degrees of that angle. So basically the advantage of this kind of structure is because it's going to be a long structure. It's going to be long distance with a relatively low structure. So we can save more material for long distance. So, and then I'd like to talk about the bridge body. So basically we have the bridge here, right? But if I were to zoom in, you guys probably could see the bridge has a lot of components. It's basically made out of 28 pieces of limestone, and then they are compacted together. And I've got we have another image here, shows clearly. So basically this is a bridge, right? And then they bend this bridge, but it's still going to be the same part. It's going to be 28 pieces of limestone, and it's going to be compacted with the iron ductile. So yeah, so if they have this structure, it's going to be really advantage because if one piece breaks, they can easily replace it as well as repair it, because they don't have to destroy like one piece breaks doesn't destroy the whole structure to collapse. And last, I will talk about the repairment of the bridge. So the bridge basically has 1,400 years of age, right? But this bridge, it's stable. Like it never collapsed, like nothing. Even though it has been designed, like they need to have more stones like repairments, but like there hasn't been any major issue with the bridge except the ornament. So they basically they replace those parts, the small parts, like they polish it like every single about 400 years, every single 400 years, and then now it just looks polished. And yeah, so the bridge is quite stable, and then that's a great advantage. That's why basically why we're really interested. And so Nina is going to introduce us why it's our objectives and motivations.
Okay, so I'm going to introduce the motivation of like why we're doing this project. So as Daniel just said, the Jiaozhou Bridge is well widely renowned for its structural stability and resilience and withstanding like 6 to 8 major earthquakes within these 1400 years without experiencing major structural damage. Yet like we're surprised to discover that although the bridge is of high reputation and widely known, it remains really mysterious, and there is an abnormal deficiency in relevant documents analyzing its basic physical characteristics. And yeah, and the exact time when it was built was like still controversial. So let alone the researchers into its mechanical performances. So in order to better comprehend its structural ingenuity and structural intelligence, investigation has to be conducted by ourselves. And we expect, while we are appreciating extraordinary seismic capacity and resilience, we can still give suggestions on possible improvements, even though we think the structure is nearly impeccable. So overall, our findings can be sort of like a reference for better conservation for this ancient architectural treasure. And maybe we can give some suggestions. And like these suggestions, like we get, we give from our analysis can also be a guideline for future arch bridge design and constructions. And since the rigidity of the soils around the base of the bridge lacks an authorized confirmation, so out of academic rigor, for every stage of the subsequent analysis, 2 different cases has been considered. So case A will be set the sides of the bridge, like of the piers, be free nodes, just assuming the surrounding soil is soft and unsupportive. So whereas case B set them as fixed nodes, assuming the soil is rigid and supportive. So I think Colenso will majorly investigate case B, and following by Queenie, she investigated case A. So I guess Colenso will share his study into this bridge.
So I will introduce the data obtained after fixing the left and the right ends and the ground of Jiaozhou Bridge. And I think we will introduce the data of only fixing the ground of Jiaozhou Bridge later. So I want to start by showing you 6 live pictures of model analysis in action. These live images are the results of analysis of each model. The red area indicates that the stress of this model is relatively high, while like the blue areas indicates that the stress of the model is relatively low. Although the structural deteriorations represented by each diagram are exaggerated, there is actually no discernible change. After this, we could look at the model 426. Model 426, when the stress cloud map changes greatly and the approximate frequency range are within 30 Hz, the whole is a deteriorated state. This is because the local seismic frequency of Jiaozhou Bridge is about 27 Hz. So you can see it experienced the earthquake in 426 model between. In addition, by comparing our data, I think it's about 0.11 millimeter displacement change. It can be seen that the earthquake has no substantial harm to Jiaozhou Bridge, and the overall model structure of Jiaozhou Bridge is still very safe and stable. Next, I would like to show the force diagram obtained by adding acceleration in 3 different directions. So let's start by looking at the picture on the left, which is the stress cloud in the x directions. It can be seen that the minimal stress is at the pier, where two fixed surfaces are located, and the maximum value is mainly distributed on the bridge deck. It can be observed that some arched connection points of the bridge and the bridge deck produce greater stress, and the stress created and generated by the big arch is larger than that by the small arch. But these stresses will not affect the stability of the bridge because the stress on the bridge is not as great as the stress on limestone. Now, let's look at the live image on the right along the y-axis. The minimal stress is still at the bridge pier, and the small arches are connected to a thicker area in the center of the deck, which can also reduce the stress. In contrast, the large arches and the underside of the pier will generate greater stress because the dynamic load on y-axis is added from the top to down. Compared with the stress value on the x-axis, the maximum value on the y-axis is obviously a little larger, but the conclusion is that even though the maximum stress has no significant influence on the stability of the bridge, the reason is similar to the x-axis mentioned above. Finally, I will introduce the stress change diagram in the z direction. From the equivalent strength of the image that the stress of bridge on z-axis is not big, the main stress distribution at the center of two large and arch bridges, and so can be speculated that the bridge has a certain ability to resist water. If the water up to the place of arch can very good help to resist impact of the currents. And then I'm going to introduce harmonic analysis. And I'm going to show you what happens to total deformation from 0 to 100 Hertz. I think this lab image might make my slide a little stark. But the important thing is if we observe this live images carefully, we can find that the bridge is shifting in 3 different directions. This is because we added 3 waves in different directions to the bridge to simulate the seismic process of Zhaozhou Bridge. Compared with the dynamic load analysis, it can be found that the bridge body is mainly to resist the dynamic load, and the design of the pier is to prevent the bridge from earthquake damage. The maximum deformation stress is always less than the maximum allowable stress, and the maximum value of total deformation is also within the basically intact range of the bridge, so it is safe. Next, Queenie would show her results.
So can you see my screen?
Yes.
So if the soil on the left and right sides of Zhaozhou Bridge is much softer than the bridge body, then both ends of piers can be set free, and the fixed supports are only at the bottom of both piers. And next, perform model analysis on the model, and the control figures of the total deformation of the first 6 modes will be shown on the screen. The maximum displacement of the first order mode is distributed on both sides of the middle of the bridge in x direction, and the displacement is in xy plane, and the mode looks like a sine function within a period. And the maximum displacement of the second mode is in the middle of the bridge, and the displacement is in like xz plane. The maximum displacement of the third mode is also in the middle of the bridge, and the displacement is in xy plane. The model looks like a cosine function within one period. The fourth order mode, the fourth order mode is a little more complex than the third mode, and the displacement is also located in XY plane, but its mode looks like a cosine function like in two periods. The maximum displacement position of the fifth order mode is similar to that of the first mode, but its displacements are not only in XZ plane, but also in XY plane. And the mode looks like twisting a tower, right? And in the sixth order mode, the maximum displacement appears on both sides of the middle of the bridge in like Z direction. And the mode looks like applying a moment. Applying a moment at the middle of the bridge in X direction. According to the results, the maximum displacement always appears in or near the middle of the bridge. Looking up the data, the seismic wave frequency in the area locating the Jiaozhou Bridge is about 30 Hz, and the frequency of the sixth order mode is about 27 Hz. So when the earthquake occurs, the mode shape is close to the sixth order mode, and the maximum displacement is about 2.1 millimeters. And next, perform transient analysis on the model. Simple harmonic functions can be used to simulate seismic waves. So firstly, the acceleration in the form of 100 multiplied sine pi x is applied in the three directions of x, y, and z respectively, which can simulate like 8 magnitude earthquake. The contour figures of equivalent stress are shown on the screen. In this case, the maximum of equivalent stress appears at the position that the toe of the main arch is fixed to the bridge section, and it is less than the allowable stress, so it's still safe. And then set the applied frequency range to 0 to 100 Hertz and apply forces of 100 Newton in X, Y, and Z directions together. Simultaneously apply simple harmonics in the three directions. From frequency response analysis, when the applied frequency is at 20 Hertz, the amplitude of stress on the bridge deck reaches its maximum value. And when the applied frequency is about 30 to 40 Hertz, the phase angle abruptly decreases from 180 degrees to 0 degree. So we just focus on the analysis of total deformation when the applied frequency is 20, 30, and 40 Hertz. It can be seen from the control figure that when the frequency is 20 Hertz, the total deformation reaches the maximum on one side of the middle of the bridge, like in Z direction. And the maximum appears when the frequency is 30 Hertz. When applied frequency increase from 30 Hertz to 40 Hertz, the deformation in the bridge changes from like upward bending to downward bending, which also corresponds to the drastic change of the phase angle from 180 degree to 0 degree. And then we are curious about whether the structure of Jiaozhou Bridge could continue to be optimized. So we build a new mode like cuboid, but which removes arch structure, and the bottom of the piles of the model is fixed to the ground, and the standard gravity acceleration is applied to it. Then a force of 10,000 Newton is applied to the upper face of the model. We select the optimization project as volume, and the return percentage was R20, 15, and 10 respectively. And the pictures are shown on the screen. when the retain percentage is 20, the optimized structure is similar to Zhaozhou Bridge, but the pier part is thinner. And there is only one small arch left on both sides of the bridge. And when the percentage is reduced to 15, the cart volume of the central part of the main arch increases. And when the retain percentage drops to 10, the middle of the main arch is opened, and the optimized structure is similar to a bridge deck placed on two arches. This is one arch, and this is another arch. When the two sides of the model are also fixed, the topology optimization results are very similar. And then let's get the summary. This picture is the case that Colanto shows, and this case is I have shown. When fixed supports are at both ends and the bottom of both piers, the vibration mode of the bridge is between the 5th and 6th order modes when earthquake occurs. The maximum displacement occurs like in the middle or both sides of the middle of the bridge in X direction. The displacement of the bridge is both in XY plane and XZ plane, which looks like twisting a tower along the X direction. When fixed support is only at the bottom of both piers, which can be used to simulate the case that the soil on both ends of the Zhaozhou Bridge is very soft. The vibration mode of the bridge is close to the 6th mode when earthquake occurs. And the maximum displacement is near the two sides of bridge in Z direction. The middle part of the bridge is twisted along X-axis. But whether both ends of piers are fixed to the ground or not, the maximum displacement is quite small relative to the scale of the bridge body, so it is safe. And in transient analysis, when fixed supports are at bottom of both piers, whether both ends of piers are fixed or not, the control figures of stress distribution are similar. The stress on the main arch is larger, and the maximum stress appears at the inner side of the pier bottom, but they are all less than the maximum allowable stress, and the displacement is within the basically intact range, so it is still safe. And in harmonic analysis, whether both ends of piers are fixed or not, amplitude of equivalent stress and phase angle have similar trends. Amplitude reaches a maximum value at a lower frequency like 10, 20, or 30 hertz, but the range we set is 0 to 100, so the amplitude reaches a maximum value at a lower frequency, where the phase angle suddenly drops, which is the natural frequency of the bridge. Compared with case that fixed connection is set between both ends of piers and the ground, the natural frequency of free ends is closer to the seismic wave frequency, like 30 hertz of this area when Zhaozhou Bridge is located, which may cause resonance. But the maximum value of equivalent stress when the bridge is in resonance is always less than the maximum allowable stress, and the maximum value of the total deformation is also within the scope of basically intact bridge, so it is still safe. And last, whether both ends of the cuboid model are fixed, the topology optimization results are similar. When the load applied on the cuboid model is exactly the same as that on the bridge model, with the reduction of the retain percentage, the topology optimization results will change from being similar to Zhaozhou Bridge and to the disappearance of small arches, and at last, only two outer arches are left but this shows that the arch structure has really high strength and safer materials. And then Selena will give us some commendation.
Okay, so from the analysis Colento and Queenie did, we found that by inspecting the nephrograms of transient response in no matter X, Y, or Z direction, the outcome of maximum equivalent stress all appears at the inner side of the bottom of the piers or the intersection areas when the foot of the main arc meets the foot of the piers. So we're thinking about consolidation of this part of structure is considerably necessary in order to further increase its seismic ability and to bear more destructive seismic waves. And additionally, the stress noteworthy concentrated on the surface of the deck, like the middle part. Oopsie. Okay. Where am I up to? On the surface of the deck, as well, since the middle part of the bridge is thin and lightweighted. So we're thinking about maybe reinforcements on the middle part of the bridge using light but materials so that it doesn't affect the overall weight of the bridge itself, while the stress it bears can be like more spread out. These are possible recommendations we can give, and it might be a useful guidance for future conservation for the Anji Bridge and refinements on its structure. And also, just as Queenie just mentioned, we found that the natural frequency of the Anji Bridge lies between 20 and 30 hertz, right? So in that specific frequency, the bridge will resonate with most drastically with the seismic wave. So that'll be like most vulnerable and most possible to undergo distortion. So, and coincidentally, according to relevant records, most of the major earthquake that Jiaozhou Bridge bears actually had a frequency of around 30 hertz. So I guess like that's just further proves the excellence of its solid structure. But still, the finding can be useful as a reference for future conservation and for future construction of new bridges. So because maybe we can be like more considerate when selecting the materials for construction so that the natural frequency of the bridge doesn't overlap with the seismic wave frequency around that region. So that will be the recommendations. Yeah. Yeah, this is another animation Colento did. So, yeah, thank you for watching. And at last, I just want to give a brief recount of like what our group had been through. So our original intention wasn't actually to analyze a bridge, but to design one, right? To design and build one. So because like most of our group members, like our major or like our intentional major are relevant to architecture. So we actually want to design something rather than analyze something. But like due to the time limits, we have to quit that design part. And like all these process discussing about like which bridge to analyze and like what will be our focus of this analysis just took us so much time. And during the entire research phase, we're just like always slower than the other two groups, like 2 or 3 days. So yeah, and since like we are unlike the other two groups, they have like Xiaokun and Ziqian. Our group members are like not that skilled in using ANSYS because like our major are not that relevant. So we actually made some like very fundamental mistakes, such as like we chose the wrong material at the very beginning. We chose like the constructional steel rather than limestone. And literally yesterday, I found that we lack some very essential statistics. So I asked Colento and Queenie to reanalyze the model for me, so like so I can complete the essay, right? So like we just hand in the essay until the very last minute, and the entire research process is just like very struggling. But like fortunately, we made it. And here I just want to express my love and thankfulness to our group mates here. And it's really good to have every one of us in this group, with Queenie doing the major part of ANSYS analysis, with Colento providing these amazing technical support, such as like doing these amazing animations, and with Daniel digging so deep into the background of Jiaozhou Bridge. And he even did an individual research into the possible structure of of optimization of the bridge. And I guess like he has already like sent you his results. And representing the entire Cambridge group, we really want to say thank you to Blair and Cindy for your consistent aid and support. And lastly, to Professor Borja for all these instructions you gave us during the research phase and for patiently correcting my poor expressions for the essay. Yeah, that's it. Thank you. Aww.
Thank you.
Yeah, that's the end. Thank you all.
Very nice.
Thanks for listening. Yeah.
So impressive. The two groups so far. I'm so impressed. Any questions from anyone? I have one just minor question for Queenie. You showed your modal analysis, and it seems to me that mode number 1 appears more complicated than mode number 3. I wonder if you can show your slide there. Your modal analysis.
This one?
Yes, I think so. If you can animate it. Okay, so my question has to do with modal 1 and modal 3. Modal 3 has a symmetric deformation. Modal
Yes.
1 has, it's called antisymmetric. You can see there, you define a full wavelength with the antisymmetric. Whereas for modal 3, you only have 1/2 of the wavelength. And it seems to me that modal 3 is simpler than modal 1. So I would expect that modal 3 would be 1 and 1 would be 3, perhaps. But maybe there are some other deformations that I'm not seeing. Just one minor comment. You see what I mean, right?
Yes.
I think
So
my technical problem. I put the picture wrong.
Maybe there is another displacement there that we are not observing. Maybe it's also experiencing sidesway motion, modal number 3, that we are not seeing from this animation. But very nice animations.
maybe it's about the angle that we see the model. In this angle, it looks quite simple.
Yeah, maybe there's some complicated mode.
Yes.
That's it. Anyone has any question for the second group?
Yeah, I was wondering just to like make sure, because when I was taking notes, so when you applied seismic frequency on the bridge, and for example, if you apply something of like 10 hertz to the bridge, the maximum point occurs at the middle. But when you apply like 80 hertz, like the maximum point occurs on the two sides. Is that because of the frequency that you applied is of the form of like a sinusoidal function? So that means the maximum strength or deformation occurs at different points.
I think so. When we do the psi function, I put sine times pi times t. So we connected with deformation with the time. So that will give us a result about an amplitude with the frequency. So we can see from the those live image. So that will show, and that would show some like red points, which is a maximum stress point. So that's just like you said about.
Okay, yeah, thank you.
So you're on mute, we can't hear you.
Professor,
your
you're muted.
microphone.
Yeah, your microphone's
Sorry. I was trying to cover up the electric fan. I was just saying, we look forward to group number 3's presentation. Perhaps we will see another hamburger.
True.
No hamburger.